All right, we're good now. Okay, welcome everybody to Innovation Insights for January 2022. Thank you all for joining. We've got a good program lined up today, and as we will for the rest of the year. Just a little bit about Innovation Insights. See if I can get my slides to advance here. Just about IACMI, we operate around the three themes of convene, connect, and catalyze, bringing people together, connecting them to each other, and then making things happen. So surrounded by a lot of these sorts of activities that occur. We were lucky enough to get back in person in October at our fall members meeting. Good opportunity for people to network and catch up, get a great tour of the scale-up research facilities you see in the lower slides, and our third presenter today will talk a bit about that facility and some of the new equipment there, as you see in the middle on the bottom. But again, good to be back in person together. We are planning a summer members meeting in Salt Lake City at the Sheraton Salt Lake. Have great networking opportunities, high-level speakers, factory tours, and other activities. And so we're planning this in conjunction with IACMI in Utah. So we expect a great show and hope that you can join us. So, what is Innovation Insights? It's our monthly webinar series featuring products and technologies from our industry members and core R&D partners. So we typically try to, in a given month, have one small company, one large company, and one research partner or national laboratory presenting in this. And any IACMI member in good standing that is a member that's signed their agreement, paid their dues for the year, can present. The webinar attendance is open to anybody inside or outside of IACMI. The idea is to get exposure for our members. They are archived on our website. So, this is being recorded and you'll be able to go back and if you've got, you see something you like and one of your colleagues can't make it, please point them to our website and then go back and watch that segment. So the dates, obviously today, January 10th, our next one will be Monday, February 14th, great Valentine's Day special for everybody. Monday, March 21st, then the April 18th and May 16th. Our members meeting will be at the end of June. So we'll get together then. Won't be Innovation Insights webinar that month. We may do, we'll kind of connect people in person there, and then you'll see the schedule coming out for the remainder of 2022. They are every month from noon to 1 p.m. Eastern time. So for those in East Coast, it's a good lunch and learn type of session. So today we've got three great speakers. And today's theme really centers around automation, from one-off to millions of parts a year type of approach. We'll start off with Andrew Hedger from Magnum Venus Products and their reactive additive manufacturing technology. Then follow that with Vern Benson from Northrop Grumman. And their automated stiffener forming and stringer forming technologies for the Airbus A350 and other aircraft. And then finish up with Doug Bradley from Michigan State University Scale-Up Research Facility, the IACMI facility there, the open access facility, where we've got some new technology that has just been commissioned for very high rate layup of tape materials, thermoplastics, thermosets, and dry tapes. So without further ado, I will quit sharing and we'll ask Andrew to present. Thank you.
All right, thank you. Let's see. Can I start screen? All right. There. All right, just loading. You guys all see that?
Yes, we do.
Perfect. All right. Well, I'm Andrew Hedger. I'm from Magnum Venus Products. I've been with MVP for about 15 years now. Doing a lot in the automation side of the company as well as closed molding. A little bit about MVP before I get into the reactive additive manufacturing. It's a family-owned company that's been specializing in global manufacture of fluid movement and production solutions for about 80 years now. So we've been around for a long time. We're located in Knoxville and have offices all through the United States and go through a heavy distribution network internationally as well. Some of the products that we deal with today at MVP is going to be kind of broken up into 4 different sections. We're going to have our composite application equipment, which you'll see with a lot of marine manufacturers, tub and shower manufacturers, where it's going to be choppers and gel coaters where the materials meter mixing, and you're having glass actually deposited out of a chopper and sprayed onto a boat. So we do a lot with that. That's kind of our core part of the business. And then we have our adhesive and sealant equipment for all type of bondings. And then we have our automation where we actually have do filament winders, impregnators, automated reciprocator panel lines to full custom jobs, engineered solutions for customers that we've done quite a few of. And then just in the last 5 years or so, we worked closely with Oak Ridge National Lab in development of a reactive additive manufacturing system, which is printing thermoset materials, who we've, like I said, worked with Oak Ridge a lot, and also Polent Composites a lot. They are actually the material we use today. So a little bit of difference. My coworker Mike likes to always use the analogy of pancakes versus butter. So a little bit of the difference is, as you all know, is thermoplastics is you'll see a lot of those printers out in the field today, but the process there with that material is basically you heat up the material to melt it down, you deposit it, and then it cools off and cures, and then the material could eventually, if you ever heat it up again, could go down to a liquid form. With thermosets, the big difference is you're using two different materials that are cross-linking and meter mixing through a gun head and then deposit onto a table, and they're curing at ambient temperature. And when they're curing, they're actually building stability and stacking up, and everything's cross-linking together as we do these prints. I'm not going to go through the whole list here of kind of the benefits we see with RAM, but it's about affordable tool productions, a lot of time savings with production and prototyping. A big thing that we like to say is your CAD file is your master mold. You don't really have to build a master mold if you don't need to. You can store your CAD file in your computer, and all you need is a step file to actually go through the slicer and begin printing. Obviously, we're printing, milling, and then just not really putting many coatings on, maybe a sealer and a release agent, and then you're ready to rock and roll in production. Some of the operational savings in thermosets is it's less risk in losing your part. And when I say that, we'll get into this a little bit more. It's going to be about kind of the open layer time that you have, because we're printing at room temperature. We're not heating this material up, and we're not having a heated table, a blower agent on it. It's all being done at room temperature, and these materials are meter and mixing together at the gun head and deposited out. And when they actually cure, the gel times can range from 15 minutes to 30 minutes. It builds that stability, and we're stacking off of those beads. So some of the advantages of printing thermosets is, again, the chemical reaction that you're getting between the two different materials is actually building a much stronger Z layer strength than you see typical in thermoplastics today. Because again, you're cross-linking these materials, and as they're curing, their materials are bonding together. There's a reduction in thermal expansion, and some of these materials have isotropic expansion. So depending on what your end case uses are and what you need to do this for, there's different materials that work for different products. The biggest flexibility, as you'll see as we go through this whole presentation, is the open layer time. And that's probably one of the major advantages to thermoset printing. You have the opportunity to actually print through previous paths when you're printing on this machine as well. So you don't have to go bead side by side. You can actually print through the previous path because it's still liquid form until it cures. The thing that's nice too, it's easy to repair. So when we actually print a mold and then we put it into production, and then say a forklift comes by, hits that mold, or we drop something on the mold and it chips, we can actually use the same material to repair and bond that mold back together and have it back up in production. So it's very easy to repair this stuff. It's durable, it lasts a long time, and then we have unrestricted build dimensions. As you see in this picture here, it's actually our RAM 48. It's a system that we just launched this year. We've been working on it for the past year, but it's our smaller scale RAM system that you can actually scale in 4x4 sections lengthwise and widthwise if you need to for larger print envelopes. Also, surface finish, we actually have different nozzle sizes that we go down to, I think close to 1 millimeter almost, that we're testing on our nozzle sizes, what our print beads could be at. So this is actually a little study that Oak Ridge did with the machine, kind of with the energy efficiencies. We were one of the most efficient energy machines that they had at the Oak Ridge National Lab. As you can see, compared to the floor BAM and the floor MVP systems, were pretty significant, a little bit more better energy efficient than all those other machines. And that's due because we're not using all those heat sources needed to heat up these materials. So something you'll see, this is our large scale RAM in a picture in your right hand corner. It actually has a pick and place system on it. We could do secondary bonding, and then it has a removable print table. So on that machine, that print table is actually moving in a Z direction. And when you need to actually remove these parts, you can remove the whole table or remove the table in 4x4 sections. So a great opportunity here, as you see in this picture, you have 3 different parts that were printed. They were all printed at the same time, and we were able to do that due to the open layer time. So if we wanted to print one mold and then pull it out, and we could print another one, or we could print all 3 of them at the same time. In thermoplastics, you'll have a tough time doing this because you're racing against that bead that you're putting down. And once it starts cooling, you're not going to get that bonding in that Z direction as you normally get in a thermoset printing. So that's something that Oak Ridge did. I think there's a table that we printed in 3 different sections there for one of the shows, but it's just showing you what you could do with that open layer time. These are the 2 different machines that we have today. The one on your right is the large scale 8 by 16 foot with a 3.5 foot print height. That is the machine that is at Oak Ridge today. And then we have our 4 by 8 machine that we have at our Knoxville facility that we're setting up currently and getting materials pumping through the systems. We actually just recently got one sold to Mississippi State, and they're going to be working with us in development and also printing parts for customers here in the near future. I think we're looking at sometime in February for delivery of that system. But as you can see, we're actually seeing a lot of people and a lot more demand going towards the 4 by 8 size with the 4 foot height print because it's scalable, like I said, in those sections that you could go lengthwise. And it's a little bit easier to access because the table is not moving up and down. So we actually could take the table and remove it, put a pallet on there or a different type of table or wood or carbon fiber or aluminum and actually print on that, so we can actually mount different types of sources down to print on top of. We use a Siemens control package on this machine as well. And we use open slicing software that we use to transfer our CAD files into print files. Like I said, we have a great partnership with Polent Composites, who we've been working with tremendously during this whole process the last 5 years. We actually started with one general purpose PRD 1520 material, and they actually are now offering more materials. They have a styrene-free material, a low shrink material, a high temp material, and we're using all these materials and pumping them through our machines today. So depending on what the need is, and what your end product is, if it's high temp or low shrink or just a general purpose, Flint usually has a great offering of materials. And like I said, we worked hand in hand with them in development of the thermoset printer and materials. So they're a great partner of ours, and we've done a lot, and we look forward to doing more with them. This is actually a video that you'll see played here. It kind of shows the thermal conductivity that's happening during the print. As you see the previous layers start heating up, because when these materials come together and cure, they start heating up, and that's when they hit full cure and become a solid. And you'll see this as I play this video of the heat and how it's just following the print pattern. I think this is actually a kayak mold that a paddle mold that we actually printed here, if I'm correct. It was at the CAMX show a couple of years ago. So it's pretty cool seeing how the heat's following up the print layers. I think about 5 to 7 layers down that is when you're tapping into materials and starts curing. And this is another video. You're not going to hear any sound on this. I had technical difficulties trying to get the sound to play through, but this is our RAM system. We launched this video at CAMX. This is a small scale 4 by 8, and you'll see on this the print through that happens on this and the pick and place that you could do. And that's what we're showing with the print through on that previous. So on that video, you got to see kind of the print through, and then the benefits of the thermosets is how you could print molds in different sections and bond them together because it is a thermoset material. You just use the same print material to bond these together. As you'll see in another slide down the road in this presentation, how we actually took two pieces and bound them together actually to get a 90-degree flange on one of the tools that we did. This tool here that I'm going to show a video of was one of the first large tools that we printed. Is over 1,000 pounds and is used for carbon fiber infusion for a marine part. So this is pretty impressive. As I said before, that we don't have to actually print on the table. We actually built a wood platform here, a pallet that we actually printed on. We're able to ship the mold on. As you see at the end of this too, we actually put areas in there so we can index the mold when we actually bring this to milling, and we can locate the mold precisely to make it a faster process when setting the mill up. And what's really unique about this print is during this print, I think it was over a year ago or so that we did this. And the unique thing is we were doing an R&L and there's a couple shutdowns and we had actually stopped running the machine for about a week. So we didn't even get through the whole print. We printed about maybe a quarter of the print, and then a facility, and they came back a week later and they are able to start printing right back up on top of this mold, and the bond was perfect. So we literally left for 5 days, came back, printed back on, and no issues with the mold. And that's the big thing about the open layer time. I mean, we really don't know how long that time is, but I mean, we went multiple days without printing on top of it, came back printed, bonded perfectly, and we had a successful tool. So that's a huge advantage. So if you have an operator, say you start print, you don't have to sit there for 24 hours printing this part. You can actually do it in 4-hour segments, 8-hour segments, so you don't have someone staying through the night. You don't have to be concerned with that. If you do want to run it for that amount of time in a row, you can do that as well. So this is a little bit about the pick and place, which is unique too, again, due to the open layer time. When we're printing and say you want to put sensors or vacuum channels into your mold, you could do that just by pausing the print, putting your locators on, putting your pick and place on, dropping sensors in, heating and cooling channels in, or even foam pieces to lightweight your product, as you'll see here. So what they're doing here is they're changing the head on the machine. It's going to pick up the pick and place head. It's going to put in a couple locators on the outside there. It's going to go change its head again after this, and I believe pick up a foam piece and put it in the middle. And this is the plinth PRD material that we're actually printing with here. This is pretty cool that what Oak Ridge was able to do with this print and pick and place and how they worked with it. And you see there that's printing through previous layers. So to show some of the end products that we actually have done, and I was talking about printing parts in different sections, is on the left side, this is actually a mold for a RV company. and you can see it's almost a wheel, like the outside part that goes over a wheel flange. And what we did, we printed this mold, and we actually printed that flange separately. And then we were able to bond that flange to the top of the mold and bond it with the same material that we printed with. And then we went to machine the mold and finish the mold and send it off to the customer. So it was nice to see that we were able to get that 90-degree angle, and that's really due to the open layer time and how we could bond these materials together. So that is a great benefit of being able to do that and actually lightweight that product. So we're taking out material and not building material all the way up that height to reach that flange and having a solid flange. The mold on the right is a mold that Oak Ridge decided to print. This is a compression mold. It was actually used on a 5-ton press, and it had a 5,000 step over on machining. As you see down in the corner where that circle is, those are heated and cooling channels that were put into this mold when we printed it. We had 180 degrees Fahrenheit of water going through the mold when it was on the press, and I think the mold surface got right around 100 degrees Fahrenheit. And then this was a pre-preg material that was used on the compression mold, and it was used for like some gas caps. But you can see there was no release agent sealer put on. It was printed, milled, and then ready for production. So it's pretty cool seeing that mold. We showcased it at the CAMX show this past year. We have it at the facility here, but it's just showing you what you could do in the different processes of vacuum infusions, compression molding, thermoforming, whatever it is, you could use this tooling for many different types of processes. In this photo, you'll see, this is actually a thermoforming tool that we used. This is one of the first prints that we did. It's probably about 3 feet by 3 feet or 3 feet by 4 feet. And what we did, we printed the mold and we machined the mold down. And then when it got to the customer, they actually were able to bond some framework to the mold. And what happened here, they bring an acrylic sheet down, and we had vacuum ports that we drilled underneath, and then basically the acrylic sheet comes down, and it's like 300 and something degrees, and then we pull the vacuum, and it forms that acrylic sheet on that thermoforming tool to match the tool, and then pops right off. So this actually was in production for a little bit, this tool, and then the process and how the thermosets stood up to the heat with no issue was pretty amazing. Some other tools that we've done, that was the marine tool that you saw that we printed. It was over 1,000 pounds. That was an infusion tool. The tool on the far right was just a hand layup tool that we did for a composite shop. And then the tool in the middle was actually a vacuum tool that we're using for pre-pregs. That's a 2-piece mold that was actually flipped over to match the other mold, almost identical to it, that they put a bladder in the inside of, and they pulled, and they're doing a pre-preg on it. But you could see though with the different molds, the finishing. So this mold was milled down, sanded, and just a sealer put on it and a release agent put on it, and then it's ready for production. So there's not much to do to get a mold to production. And a lot of times people will see this. A big difference in the thermosets and thermoplastics is our print time may be a little bit longer than what it takes to print a thermoplastic part, but our milling time is cut in half. So that print up in the left-hand corner took about 70 hours to print. It only took 24 hours to mill. Because when we're milling, we're not worried about that head bringing up that heat and that temperature so much and impacting the material. On thermoplastics, you have to go slower because that heat could deflect the materials and make it melt down. So when we're machining this thermoset, we don't have to be concerned with that. So your machining time is a lot faster on thermosets than you'll see with thermoplastics. So that's basically what I have for the slides today. We did have a launch of the Ram 4x8 this year. It's at our facility in Knoxville, Tennessee. We also have the 16x8 machine at Oak Ridge that they've been a great partner with us in helping develop this. And then, like I said, Flint Materials has been a great partner as well on the materials they offer for the thermoset printer.
Thanks,
so
Andrew.
If there's any questions, no problem.
Yeah, thanks, Andrew. I've got a couple questions that I want to try to get through quickly. To prevent sag, is there a thixotrope or something in the system? Yeah, is there something in there to keep it from flowing too much?
There is a little bit of filler. I know. I let Blaine answer that question. Actually, they do fill the material up with some glass and some of the stuff to keep kind of the thickness from it sagging and stuff and being able to stack up.
Okay.
I'm not sure about all the details on that. That'd be more of a question for them on the material.
And there's some sort of either milled glass or something in there to give it some additional strength. Okay.
Mhm.
All right. Sounds good. If anybody has any other questions, please put them in the chat or in the Q&A, and then Andrew will be monitoring them for the rest of the hour, and we can and answer those. So we need to move on to our next presenter. And our next presenter is Vern Benson from Northrop Grumman in Utah. I've known Vern since, well, I shouldn't say how long, but he was a pioneer in the development of some fiber placement technology when I first met him. And he's gone on to create a lot of different automation systems at Hercules, and ATK, and Northrop Grumman as it's gone through its various iterations and ownership over the years. Vern hasn't moved, but the company names has changed. So Vern, I'll turn it over to you. You just need to put it in the slideshow mode, and we'll be ready to go.
Okay, does that show up okay?
Yeah, you need to do your swap as you did before under display settings.
Okay. That work?
Perfect. Yep, we're good.
Okay. I appreciate it. Let me jump to the next slide here. I'm just going to give a quick intro of Northrop Grumman, our Aerospace Structures division, talk to you a little bit about evolution versus revolution in the technology area, and then give you a brief overview of an automated composite stiffener forming technology that we think is revolutionary. And then talk about a few applications that we are using that in today, and a little glimpse of where we're going with it in the future. So, as part of Northrop Grumman, we got purchased by Northrop Grumman. We're formerly Hercules, and then ATK, Orbital ATK, now part of Northrop. We are part of the Aeronautics Systems group. Aerospace Structures is what we are. They also have a Defense, Mission Systems, and Space Systems group as well. Our Aerospace Structures business unit, as we're called, we are a merchant supplier of composite structures to the industry. So we do have a commercial segment where we supply products to commercial aircraft and other commercial ventures. We do have external military customers where we supply composite products to even competitors to Northrop, the other companies. And then we have our internal Northrop work that we do in the military area. And then there's a missiles and launch segment. We're primarily involved, our group now is primarily involved in the launch part of the business. So just real quick, evolution versus revolution, there's some, every so often in the industry, there's a major breakthrough where you really make a major fundamental change in how we make product or process. And then more often is the evolutionary change where we're continuously changing, improving things that we have developed. And so I've had the privilege in my career of being involved in a lot of evolution, but also a few what I consider revolutionary steps where we've been able to make a pretty significant impact on the industry. And so I'm just going to touch on a couple of those, and then we'll touch on the stiffener forming. So, my early career was involved with filament winding, which I think is one of the first revolutions in composites automation. The ability to automatically put down material to do rocket motor cases and large cylinders, things of that nature. So we've been very involved in that from early on. The other one was automated tape laying, going from hand layup to a system that could put down wide layers of pre-preg tape. That was pioneered early on by LTV and VAUD, and later Cincinnati, Millicron, and Ingersoll. We do incorporate ATLs in a couple of aspects of our factory automation today. But the big one for me was involvement in then trying to get a system that could handle more complex geometry. So the automated fiber placement to me was a revolutionary impact in our composites lamination industry, and had the privilege of being involved with the development of the first fiber placement machine and ongoing machines. and then involvement with Cincinnati Millicron. We do have a large dockable, this one in the middle here, large dockable gantry system that can do both tapling and ATL, AFP and ATL. And then today there's some major improvements with, this is a large machine with Ingersoll, and you see a machine here with electroimpact, which electroimpact really pioneered the dockable heads to go with the machines, and then the industry's kind of followed that as an evolutionary step. So the one we're going to talk about, the main topic of the pitch today was automated stiffener forming. We call it ASF, a new automation technology that we brought online here several years ago. That's the ability to make the small detailed parts in an automated fashion, and that was a technology that was lacking. We could do large acreage structures with automated tapling, automated fire placement, automated film winding, but to do these smaller detailed parts with any kind of automation was lacking. And so we took on this challenge several years ago and developed what we call an automated stiffener forming process, and started out making stringers, long stringers that turned out to be fairly complex with pitch, yaw, roll configuration to them. We evolved that technology then into being able to also build frames, curved frames that go into an aircraft fuselage, for example. And then we also evolved that further to do automated forming of engine cases with integral turned up composite flanges. So that's kind of an example of going from a revolutionary technology and evolving into other areas with that similar technologies. So real quick, this is the basics of our automated stiffener forming process. Is we have a supply head where we have material spooled up. The material already has, it's a continuous roll of material, but it already has the angle orientation established on it to be put down on the stringer. So it might be a roll of plus 45-degree material or a roll of 90-degree material. But anyway, it comes up, and we have a separate process that actually develops those continuous rolls of off-angle material. And then the material comes off the spool. This is the example of an Omega or hat stiffener. So the material comes off the spool, it gets tacked onto the cap of the Omega, gets compacted across the cap, and then there's another. This is like a train of forming systems all together that move as a unit, which we call the forming head. So the material comes down, gets tacked, gets formed over the upper radii and down the web wall, and then there's rollers that come along compacted along the web wall. And then we have another set of rollers that come behind it and actually compacted into the female radius. And then the combination of squeegees and flanges that smooth the material out and compact it onto the flanges. And then this has a carrier material on it that protects the material while we're forming and shaping it to the shape of the tool. And then we take that carrier material off after the material is formed into place. That allows us to make these complex stiffeners. Here's an example of a couple of machines in our factory. And this is an example of one of the larger production machines. In this case, we hold the delivery head, forming head fixed, and we actually move the tool underneath the system. We have another machine that does it the opposite way, that the carriage and the forming systems move. This is an example of this train of individual roller elements that are going along and forming, compacting the material down the length of a stringer. So that gives you a quick idea what we call our linear machine that makes long, complex stringers for stiffening wing skins, fuselages, things like that. As I mentioned before, we evolved that also into making curved or frame type components. And you'll see here in the lower left-hand corner, we have multiple heads that hold different orientations of material. The robot picks it up and actually places that onto the machine itself. And the machine places the material usually on one flange of one face of the frame, and then the forming segments come around and form it across the web and up the back flange to get a Z stiffener or a Z frame, as you see here. So it's again an automated placement and automated forming system to get these kind of structures. So examples of application on the Airbus A350 aircraft, commercial aircraft. We make stringers and frames in production for them right now. We make about 60% of the frames in the fuselage and and pretty much 100% of the stringers that stiffen the fuselage section. So there's over 684 parts per ship set. It's actually gone up as we've gone we've added the Dash 1000 component to it. That's actually a little higher. But we, again, we do stringers and frames for those aircraft. And at full rate, at a 12 aircraft a month rate, we're making about 25 miles or 40 kilometers worth of stringers, stiffeners per month, going through this equipment. So that gives you an idea of the capability and the volume involved with that. So, and I mentioned also the case forming. So we also make engine cases. This is an example of the rear case on a Rolls-Royce engine, made out of composites with integral turned up flanges. We have a couple of different programs. Again, this is an evolution from our automated stiffener forming technology, using similar progressive roll forming process to create these complex shapes in a very efficient manner. And then just to give a quick idea where we're going, we are also taking, so I've been doing most of this work with, we did some early work with most of the production work is done with thermoset materials in the last few years, and we have now evolved the technology for doing dry fiber formats and creating dry fiber preforms to be used with resin fusion type processes. So we're using different kinds of dry material formats, dry wovens, dry NCFs, high tapes, braids, and even some commingled material. So there's a lot of players introducing materials into this arena, and then we are adapting those materials with our automated stringer forming processes. This is an example of an Omega, again, an Omega stiffener. This happens to be done rather than forming it onto a male tool, we're forming it into a female in this case, per the request of our customer. And it shows the ability to place, form, create a consolidated preform that then gets taken and interfaced with the skin, and then the whole thing gets co-infused together as a co-infused and cured stiffened skin and stringer structure. So anyway, we're working that area, also working a little bit in the thermoplastic area. So these are some examples of things we're doing in the automation of composite stiffeners. These are all highly reinforced carbon epoxy in general structures that we're developing and introducing to the industry. So with that, I'll leave it at that. We can take a question or two if there's time, or we can move on to the other presentation.
Yeah, we've got a minute or two if we've got any questions. Obviously, this was developed for aerospace, but do you see applications in other types of commercial vehicles, say over-the-road tractor trailers, frames for those, or rail cars or buses, anywhere you might need something. And I believe you can, like you say, you can jog it, so it doesn't have to be a truly straight structure, right?
Yeah. So we have the ability to do some joggles, some pitch jaw and roll. And yeah, we are actually looking at a possibility in the large tractor trailer type structures. So
yeah, and you're not limited to carbon fiber, obviously. You can do glass fiber prepregs, or glass or carbon fiber non-wovens, NCFs, or fabrics.
Yep, that's correct. Yeah.
Okay. Yep. All right. Appreciate that. Thank you very much, Vern.
Okay.
It's just fascinating technology, the way that it's evolved over the years. Okay, keep us moving on schedule. We'll move to our third speaker, who is Doug Bradley with Michigan State University Scale-Up Research Facility in Detroit. I know many of you have had the opportunity to maybe visit that facility, but if you haven't, here you'll get a bit of a tour here. You'll get to see some of the capabilities there. And in particular, as we move up this volume scale from making one-off that Andrew discussed, in the tooling area, to 25 miles of stringers per month, then we're going to talk about how do you address the high volume automotive equation, where you need 100,000 or more a month of something. So Doug, over to you.
Yeah, thank you so much, Dale. Yeah, just give you a little bit of background. My background, I've got a kind of an eclectic mix with some aerostructures. I worked Lockheed manned space flight stuff, did a little bit of work in chassis at Ford, all composite material kind of things. And then did 6 years in that, worked for a tier 1 with Plasan on some Corvette stuff. And then I came over to MSU here. So I'm kind of a composite junkie. If it flies, dries, if it's a train, as long as it's composites, I like it. So what I'm going to go through, kind of a little bigger picture, ATL, AFP, just to level set us. Vern did a great job on that, and Northrop, ATK, Orbital have been leaders in that for years. We did some technology benchmarking more from an automotive perspective, kind of the needs there, they're different. And we'll talk about those. And then I'll go into the SURF ATL capabilities that we've established here at SURF, and then kind of back up a little bit more, and I can go into some complementing technologies that we have here that could be used to supplement ATL kind of work or other things. And I just pulled, a couple of composite vehicles. The bottom left corner is a Ford GT. The build volume there is about 1,000 units total. The next vehicle in, that's Corvette C8. If you looked, depending on the year, they kind of go up and down in their sell rate. But C7, C8, you're probably talking about 30,000 units a year, somewhere on that. When you start the next picture over, the Ranger, if you start looking at like F-150, you're probably talking hundreds of thousands of units a year. If I lump in F-250, 350, you're probably in that 400,000 a year to 500,000. So when you talk about composite articles on vehicles, that technology has to change, and it's it drives you to different solutions. The bottom right hand slide grab, when I worked the shuttle system, we were building 10 a year for the nose cone, which is the middle vehicle. And when you go to the Hyundai Uber kind of agreement, their partnership, don't know how that's going to shake out on volume, but that'll be a different solution. And so when I think of ATL, AFP type technologies, I gotta move my thing so I can start this. The technology mid-'80s came out. Vern's a leader in this technology, but from an automotive perspective, I was happy if we could get one fiber placed article off in 24 hours. That's great. That doesn't work for automotive perspective. The other thing that doesn't really work is if I have to use a lot of consumables like bagging materials or separator films or things like that, that really hits my cost from a part perspective. So I want to try to minimize that and avoid it. So if I go to the next slide, from an automotive needs, you know, the drivers and what automotive processes really look for is, you know, having a balanced process, and I'll talk more about that, but also fast cycle time. So I need to get out a part. If I can hit a part every minute, then I can support off one set of tooling, you know, rough around 85 to 100,000 units a year. And the other thing, I need that process to be very robust and reliable. So it can't rely on an operator with either a placement of a thing, a touch. It's got to be from a very wide process window. So I can move side to side in that window, but I still get a good quality part out. The minimal waste, I talked a little about minimizing the consumables. At the time I was at Plasan, I think we were spending about over $1 million on just bagging material alone every year. The part cost, when you start looking at, you know, bidding on a project and quoting on a cost, it's largely dominated by my material cost. So if I can minimize my scrap, minimize, you know, place fiber exactly where I need it and not have, you know, over trim, off fall that gets thrown away, that really kills your cost. The other thing is, from an automotive need, minimize tool sets. And that does two things. One, it's a less tooling investment, but also if I have 20 sets of tooling to give me my volume every year, that means I'm using, or I might have parts stuck on those tools. If I have a problem in the process or scaling it up, then I've got a lot of work in process and a lot of scrap rate. I'm going to go to the next slide and talk about flow rate. So that flow rate, the ideal automotive is you're bringing material in, and this is I borrowed a chart from some joint work we did with Dura on a seat back. So this is their chart, but illustrates the point. I'd like to see material coming in, and hopefully you can see my mouse in the top left corner. Material coming in the plant on one side, flowing to an operation like a tape layup operation, you know, robotically moved over. So I don't have, you know, 100 parts between that tape layup operation and the next, if it's a net forming operation or a drilling operation, whatever. I want to see nice flow, you know, start in one corner, move around my plant, and then go out the shipping door, and no parts in between. That's the ideal. It doesn't mean you can always do it, but that's the goal. And so it minimizes any problem I might have. I catch it right away. There's feedback into the last operation and just better flow. So that's an automotive requirement. The previous project team consisted of, it was really a very good working thing. We all came to the table, we had expertise, level set, everybody had an equal weight in things, but between the industry partners, Ford, Dura was the tier one, and BSF was the material supplier. And we went through and established a criteria for the tape laying technology from an automotive perspective. And these are just a few sample things out of the weighting criteria, but you know, throughput came to the top, tailorability for different blank shapes and sizes, near net shape, you know, minimizing the waste, doing the ability to do any or multiple layup angles, and then the amount of capital investment it would take for the throughput you got out of that machine. So all those were boiled down into a criteria matrix weighted by the industry partners, and the decision matrix that came out of it was down selecting a fill technology. Phil's a company in Austria, and that walks me right into this. So this is, I'm just gonna, I'll roll through this video and I'm gonna talk at the same time. So I'll let that spool up a little bit. But this will go through, and the video is gonna show the multi-layer capability. This is the machine that we down selected. This isn't the exact machine. Ours has 12 heads. You can get up to 16 on this machine. But the throughput, the requirements we built in were, we wanted this to make a 48 by 48 inch blank, do 6 plies, any angle, and it had to do it in a minute. And so the spools here you're seeing, those are, as the machine's running, you could load a new spool, you push it in, it'll automatically load and swap out. It notifies you if it runs out and comes over and swaps it out. The traditional tape playing technologies that I showed earlier, those you have to pause, change out. I think they've added some capability to do that automatically, but this is a lot faster. We commissioned this machine in last December. We ran glass PA6 and carbon fiber PA6. We pushed on a lot of different, you'll see it in my charts coming up. I pushed on some different geometries. We pushed on different angles, doing splices, went up to 17 plies thick, and they're ultrasonically staked. The machine will do thermoplastic and thermoset. And as Dale said, it will also do dry, but you just have to have the right binder material in the machine to do that. And we haven't pushed on that yet. Most of the work that's been done to date has been in the thermoplastic realm. So if I look at the flow for this rapid ATL process, what we've demonstrated here, you walk through at the top right. So I start out with material tape, 50 millimeters wide on a spool, and then load that in the machine. From there, the ATL, you generate the shape of your preform, what you want that to look like. Here, this is just one we use for commissioning. It has a serpentine pattern on the right, and I cut a window out of the center of it. And then the tape placement, you tell it what angles, and it'll automatically generate ultrasonic stake points. If you don't like them, you can move it or specify them at a different interval. And this is the generated preform out of it. So that's a non-consolidated preform. It's just tagged together with ultrasonic stakes. And then from there, depending on how this is one process. You could consolidate that in a tool if you wanted to with some shape. We did it with a double belt press. And then got a big laminate that I don't remember. This one, we did 2 different thicknesses for this application. One was 2 millimeter thick, one was 3.5. This shape here is a 3.5 inch or 3.5 millimeter blank. But you water jet them out. Then you've got an insert that could be placed into certain areas and over molded with another material. So an injection molding process. Other type processes, you do a tweak on that. You could take the ATL preform and then form it. And we did this for the project with Ford Endura, where we formed it in some rapid prototype tools and into a 3D shape, then secondary drill these. And the light green inserts are where you see them in the application. So there's a dog bone here in the seat pan, and there's 2 dog ears in the seat back. And that's a bonded assembly. But if you take a look at the cross section through the laminate, not quite up to aerospace standards, in my opinion, but from a big acreage, automotive could live with that all day long. Not too many voids, resin-rich areas look pretty good. This was just a rough trim we did here in the lab, but so we're pretty encouraged by it. I'm going to go into this next slide and just kind of back up and give you an overview of our facility, where we're located. It's in the Corktown area. We've got about 50,000 square feet of space, and everything in our building has been put in place based on industry pull. So we haven't put, if there's a need, if there's a gap, then we went and with industry either helped down select it or they requested us to put it in. All the personnel in our building all have an industry background, about combined 120 years of experience in composite material areas. The type projects we do are for prototype development, run at rate validations, scaling up technology before it goes into an automotive plant, where you can't, two things, it's difficult to break into production to try some things. I don't want to, have to run on a Saturday, or sometimes you want to run under the radar to, kind of prove out your process. You could leave something set up here, not have to worry about doing a tear down, reset up, things like that. This whole facility established with funding from MEDC, Oak Ridge, Department of Energy, and MSU just manages the contract, and we're that's all I'll say. So other processes we have here at this facility, Schuler press, and I'll go into this in the next slides. 4,000 ton Schuler press for large part development. This is an injection molding machine, which did those seat backs that were shown in the chart. We also have a pre-preg line here, and we've got various different tooling sets. Fender tool, you'll see in a video in a little bit. These are two tonneau covers. This is a Volt battery tray that was donated by GM. So one happened to be donated by Sabic. And the seat back tool is also, there's two tooling sets with that. So from a compression press capability standpoint, can be used to consolidate ATL blanks, could be used SMC, liquid compression molding. We've done some of that here as well as high pressure RTM. Different than RTM, this high pressure, you're talking injecting, hundreds of bar in your cavity, very high, 1500 PSI. Press also used for thermoplastic forming. Go to the next one here. We have an injection molding cell. It's a Millicron. And this is a seat back tool that was used to generate some of the parts in the previous slides. So it's a 3,000 ton machine. This tool happens to be a dual cavity. Here's your shot sizes. So it's got a range. We've got a couple different barrels too that you can swap out. Typical processing temperatures right now we can run up to about 550, 600 F, somewhere in that range. Sorry. And we have robotic handling to unload and load the back of the machine, as well as sequential valve gates, which control the flow of the material into the tool. There's also some capability that's planned to be installed. It's under contract now, being installed with preheating blanks and overmolding cell. There's also a planned upgrade on this piece of equipment for water assist, so you can do hollow parts. And another Shane who works here also, he's in charge of that, so he's heading that up. Pre-preg line capability, we have a small 12-inch wide pilot line, and line speeds 3 to 30 feet per minute. Typically what we've done here for material suppliers is epoxy development, a lot of the snap cure type systems, and that's another piece of equipment that could be utilized. The high pressure RTM machine, this machine here is integrated into the Schuler. And it typically infuses a cavity, depending on your tool side, in about 15 seconds, compared to the traditional RTM, which you're talking 20 minutes, depends on my part size. Also can be used for liquid compression molding, where you're robotically dispensing your resin over top of a preform and then shuttling that in the press. This piece was commissioned June of 2019, and we've run a couple different projects on it. It's capable of epoxies and urethanes both. Traditionally here we've stuck with the epoxies. We've got a project that will be moving into the urethane systems here in the next little bit. It is tied into ventilation systems in case of running some more exotic materials. Also, it has mix on the fly adjustment, and you have the ability to tailor two streams in the side along with your A and B ratios. So for IMR or pigment or varying catalysts on the fly. Let's see. Two other pieces that I'll quickly mention. We have this piece is a 32 millimeter twin screw compounder. It's actually owned by Ford, but we have an agreement to use with them. They've consigned it with us. And we also have plasma treat in our facility that can be used for various different studies. In complement to support all those things, we really don't get too heavy into the analytical chemistry side of things, only from the side of more of a process control QC kind of check. We have some FTIR, DSC, DMA, and you saw some my photomicrographs, can't say it, that I took earlier. Some basic trimming, cutting, grinding, and then a controlled lab where we do a lot of the humidity control, the pre-preg kind of stuff like that. So that pretty much summarizes kind of what I had to go through, give you an overview, kind of some capability we have here in our lab, and really appreciate the opportunity.
Thanks, Doug. Appreciate that. I want to say thanks to all of our speakers, to Andrew, to Vern, and to Doug, and walking us through some of the latest innovations in automated processing of composites. We've hit the end of our hour, so we don't have a moment here to take any other questions, but be sure to tune in next month on February 14th for our next edition of Innovation Insights. And don't forget that all of our episodes are available on the IACMI website at iacmi.org. So thank all of you for attending, and we will see you next month.
Thank you.
Thank you, Dale.